Charles is founder and CEO of Future AI, who are very kindly sponsoring today's conference. Charles Simon is going to share his unique insights on AI, AGI, and creativity. His background in electrical engineering, computer science, and neurosciences give him a singular viewpoint. Having observed and participated in AI development since the earliest neural network conferences, he's also able to add a historical perspective. Founder and CEO of Future AI, developing software which will form the necessary components of an AGI future, including the open source brain simulator 2. Many of you will have seen his demo, his exciting software over the last couple of days, and we've been having really a wonderful time with some great discussions with Charles. So I'm very delighted to welcome Charles on stage at AGI-22 in Seattle.
Thank you. So you come out on the stage like this and they've always got a slide with your name on it. You think that that's for the audience benefit, but it's actually so I can say, oh yeah, that's what I came out here to talk in. And the clicker works and everything. And I'm still Charles Simon on this slide, founder of Future AI. And I'm going to talk to you about a number of things that we're doing. AGI to me is the most exciting project on the planet because not only do we get to do a bunch of cool stuff with computers, but we get to probe the mysteries of the mind, a question that we've been addressing for millennia. And of course, this has always been the holy grail of computer science since, I guess, the 1950s. And with a little luck, we'll be able to save the world. And that's a combination that you seldom get in a project that you get to work on. And so today I want to talk about creativity and a little bit about what it would take to create an AGI. And the way I'm going to approach that is to scope the size of the project. And, you know, there are estimates of it's going to be 100 years or it's going to be next year or whatever. And I fall on the earlier area of that spectrum, and I want to explain why that is. And along the way, in order to get you to believe me, I need to propose some sort of structure for AGI. And then I'm going to talk about the conclusions that you can reach from this proposed structure, because it's not the classic AGI structure. So hopefully you'll be able to see some things that you haven't heard already 100 times in this conference. But creativity, of course, the original creative idea was you put 100 or 1,000 monkeys in a room with 1,000 typewriters, and they type away, and they will eventually type all the works of Shakespeare. And I've got this image in my mind of Shakespeare standing reading this stuff saying, gibberish, 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 nonsense, gibberish, gibberish, nonsense. To be or not to be, hey, this is hot. But the creativity, of course, isn't in the monkeys, and it isn't in the typewriters. The creativity is mostly in our friend Bill, and to some extent, the guys who had the idea to get all of these monkeys and put them in the room and buy the typewriters. That's a big part of the creativity. And of course, you've seen already in this show a lot of DALL-E pictures. And I've got mine. I put in the words creativity as at its best, and this is what I got. And I thought this was pretty good, but we've seen a lot of DALL-E pictures. But again, the creativity is in the guy who wrote the program or the team that wrote the program. This is, by the way, out of Crayon. And if you haven't been to that website, it's a lot of fun. You can put in the words and it'll draw the pictures. But the creativity is in the guys that write the program and in you selecting which picture you want to keep and which you want to discard. The same is true for GPT-3. And in this case, it's been asked to write a poem. And from my perspective, this isn't a very good poem, but maybe it's a better poem than I was going to write. So who am I to complain about it? But we've had a lot of talk about that. But I want to give you a creative assignment mentally to say, create a rhyme on this image, and then we'll talk about, well, what did it take to do that? And you might say, a fat cat ate a rat. You might say, 'tain't fittin' for a kitten to eat a mitten. If you were in Spanish, you might say, mato un gato con nitrato. Google Translate says that I kill a cat with nitrate. I don't have much Spanish myself. But now you think about what it would take to have an AGI do such a program, and the first such a problem. And the first thing you do is you start breaking the problem down into its components. And you say, well, I need some sort of image recognition. And of course, I want to be able to recognize an image like this, which of course doesn't have anything to do with a photograph of a cat. This is a sketch that kind of captures essence of cat. And thus far, although we've got great image recognition programs, they're not really very good at capturing the essence of something. And I could ask you, is the cat happy? Looks pretty happy to me. So you're going to want to write some sort of cheerful poetry. We're going to need some sort of system for understanding the sounds of words in order to make some rhyming. We're going to have a system that understands the syntax, so I make something that makes a little bit of sense, even though a fat cat ate a rat doesn't make a lot of sense. And then you're going to need the system to decide what it is. And of course, all of this is based in a context, because you might write a different kind of a rhyme if you were standing up in front of people at an AGI-22 conference. If you were writing for the locker room, maybe you'd create a limerick and it would have a little bit different flavor. And you go down this road and you've collected these ideas and you're going to come up with a narrow kind of AI program, and it might work really well for this specific application. You've made very little progress towards AGI. And so what I want to do is to kind of broaden the concept and think about, well, what is overall general intelligence, and try and get ourselves out of the pickle of creating many, many narrow projects and hoping that at some point in the future they grow together, because although they might, and I don't say it's impossible, they haven't so far. And I'm hopeful that we'll put together an architecture that will form a basis for a kind of a universal intelligence. So now we're going to talk about, well, how big is the problem of creating AGI? And I want to address that from a number of different perspectives, of which you got this preview of the Jacquard Loom. And the Jacquard Loom, how many of you are familiar with the Jacquard Loom? Okay, the Jacquard Loom is a very first programmable device. And it had these punched cards, and the punched cards would control the mechanism of which threads were raised and lowered while the weaver was just running the thread back and forth through it. And so the punched cards would define the pattern that was going to be produced in the fabric that was coming out. And so the input, of course, was a punched card. The output was the woven pattern. The program size, and I'm just looking at the size of the cards and the approximate number of holes I can see and say, well, that's probably thousands of bytes of information. And of course, now we've gone on to the world of the computer, where the input is a program. The output can be almost anything. Of course, you also get auxiliary input coming into the side of this, not just the program, but you did in the loom too, because the weaver got to choose the color of the thread, etc. But in the program, this program size can be gigabytes. We're now to a point where you can put together a team of software engineers and produce massive, massive programs. But you don't usually think about this, but in a similar vein, you can grab human DNA, put it into the appropriate kind of a human cell, and out pops a person. And this person not only has a human body and a human structure, he's got a human intelligence, at least the starting of a human intelligence. And the total program size of the DNA, 750 megabytes. And when the Human Genome Project was getting started, this was an unfathomably large amount of data. Well, now you can put it in a small corner of a thumb drive, so it's no big deal. And yesterday I asked John Cadwell, well, how much of that 750 megabytes of data is actually controlling the structure of the brain? And the answer is, we don't know. And one of the reasons we don't know is that the structure of almost any human part is largely dependent on its chemistry. And then there's also this structure, and we have a much better idea of how DNA goes to chemistry than we have about how it goes to structure. But obviously, somehow the DNA defines what the structure of a person is, and part of that defines the structure of the brain. And we'll talk about the structure of the neocortex, which is what we think with, we think. And maybe that represents only 1% of that DNA, maybe 10%. We really have no way of knowing at this point. But that means that we might be able to define a complete AGI in a program as small as 7.5 megabytes. And 7.5 megabytes is a program that's well within the scope of a team to write in a couple of years. It's really not that big a deal anymore to write a program of that size. And I want you also to consider that a horse with significantly less DNA has many capabilities at birth that humans don't have. The horse that's newborn can stand up and walk and see obstacles and not run into obstacles. And if you've ever gone down the road of trying to write a program that does that, you know it is a big deal. And so you also know that DNA somehow is capable of defining the neural structure that allows that to be taking place. So the AGI problem, as I see it, is one of, well, what are we going to write? We just don't know what to write in our 7.5 megabyte data set. And we have no problem with how massive the program's going to be, because it's not going to be that massive. And we don't really have a problem of how fast or vast the computer is going to be that's going to run this program. And I'll talk more about that a little later. So the question is what to write. Suppose you knew exactly what to write to make an exact human brain. And so imagine you spend 2 years coding it, and then you start training it. And if it's exactly like a human, after 3 years of training, it's going to have the capabilities of a 3-year-old. Now, I like 3-year-olds as much as the next person, but they are not particularly marketable, at least in our society. And so we're going to have to wait longer to get some more general intelligence into this person so we can make some more use of it. And we can expect maybe 20 more years of training and experience to get somebody who's really going to be useful and generally intelligent. And we just don't want to wait 25 years to find out if our idea was correct. So we're going to take a bunch of software shortcuts, and I'll itemize some of them. And it's kind of interesting that we started when I was an undergraduate. There was a big push to create chess playing programs. And there were a lot of people that believed that if we could solve a chess playing program and write a good a program that would play a good game of chess, that the rest of general intelligence was going to be easy. And that turned out not to be the case. And this is codified now as Moravec's paradox, where the capabilities of an adult are much easier to program than the capabilities of a 1-year-old. So we're going to be looking for a lot of software shortcuts. We've got a lot of capabilities, a lot of possible approaches to AGI, and I'm going to show you what mine is. And my approach is to say, let's go back to the only actual general intelligence we know about. We're going to talk about the brain. We'll look at the neuron. And I wrote the brain simulator so I could simulate a bunch of neurons and learn what sorts of things you could do with neurons. And the brain is largely constructed, largely split into 3 general areas. And some of these numbers are going to be important, so I'll ask you to remember them. The brain stem is full of autonomic functions. We don't think that it learns. We think it's hard-coded because nobody seems to have to take the time to learn to get their heart to beat or to learn how to breathe. That seems to be hard-coded. The cerebellum, back here, back of your brain, kind of underneath, is believed to be responsible for coordination and muscular coordination, so I can talk and walk at the same time. and 56 billion neurons. About 2/3 of the brain is, in terms of neuron count, but not nearly in terms of volume, is involved in coordinating muscles and learning sequences of actions. And so, for example, if you were to learn to play the piano and you practice over and over and over, that area of your brain learns by repetition. And the neocortex, the whole top of your brain, is what we believe is the thinking part of your brain, is only 16 billion neurons. You got to take only 16 billion with a grain of salt. And it learns by a whole number of different mechanisms. But it's kind of interesting that the brain is largely split fore and aft. The neocortex split more fore and aft, that all of the sensory stuff for the most part comes into the back of your brain. You've got visual cortex and auditory cortex, et cetera. And the forward part of your brain is involved in planning what to do and doing it. And this is a very rough cut, but bear with me on it because we don't want to get too far into the details. But so, for example, the part of your brain that recognizes speech is back here in the sensory zone, and the part that generates speech is up here in the action zone. And right across this area are the motor cortexes that control all of the voluntary actions, and the sensory cortex that receives all of the touch and pain sensors from your brain. So looking a little deeper, let's look at an individual neuron. And of course, as I say, there are billions of them. And so they are hooked together in a big network. And we have these wonderful graphics now that we can do. But the individual neuron generates a spike. The spike travels down the axon, goes to the synapses, connects to the other neurons that it's connected to, and transmits a signal. And of course, I'm making a grand oversimplification because, like all biology, things are much more complex than they appear at first. But the signal travels down the axon at a leisurely approximately 1 meter per second. This is not an electrical signal. It's a kind of a chain reaction of ions going from place to place. And so the neuron itself is an extremely slow device. And here's what you learn. If you play with neurons in a simulator for a couple of years, you learn what neurons are really good at and what they're not so good at. They're really good at signal differentiation. For example, in your eye, you can detect boundaries of various colors or brightnesses with considerable accuracy. And this is looking at adjacent neurons and considering their firing rates as being slightly different. And you can do that with a lot more accuracy than you can know the absolute firing rate of any neuron. And this is a source of a number of very interesting kind of optical illusions. Similarly, you can detect the arrival time of multiple signals, and you use this for directional sound. And for example, sound coming from over here will come to this ear about half a millisecond before this ear. And in your brain, you can do that quite effectively. In fact, the auditory people tell me that I can detect the direction of sound accurately in front of me to the accuracy of about 10 degrees. And this represents deltas in arrival time of as little as 10 microseconds. It's amazing how accurate this can be. So you can have short-term memory in neuron firing or in the charge storage in a neuron. And I'm talking about really short-term memory, a memory that you can establish with a single spike. You don't have to do any synapse adjustment. You can store something for a short period of time in the state of a neuron and have it happen instantly. Long-term memory in synapses The neat thing about synapses is that they can store memory in the configuration, the physical layout of the ions in the synapse, and this requires essentially no energy to store indefinitely. And so you can learn things now and set them up into the configuration of the weights of your synapses and store it indefinitely without burning any energy doing so. As opposed to neurons, if you want to fire a neuron, that does take energy. And so anything you're going to store in a neuron firing rate or in the charge of a neuron is going to take some energy to maintain. Neurons are really, really slow. And here we're talking about time frames of 4 milliseconds. Now, when I was an undergraduate, this was in the time when telephone switching was becoming solid state, and we had all of these telephone relays that you could get for dirt cheap, and we built a CPU out of telephone relays. Telephone relay switches in 12 milliseconds. 12 milliseconds is only 3 times slower than this speed, and you can get faster telephone relays. So when you're thinking about how the brain works in terms of its speed, we're thinking of 1950s telephone relays. The brain, the neurons in your brain are so slow, this has a dramatic impact on the kinds of structures that might possibly be created. Likewise, we talk about the synapses, and you typically will see you can set the synapse weight with this nice orange curve, and this is called Hebbian learning. And then you look at the underlying data, and there's all of this scatter, which says to me that it's essentially impossible to set a specific synapse to a specific weight in a short period of time. Essentially, in order to set a specific weight, you're going to have to tweak and adjust and this and that, because a single spike is not going to be doing it for you. And what that means, these slowness and these weight problems mean that you cannot represent very many distinct values. Because if you, for example, want a firing rate of a neuron to represent a value between 0 and 10, you're going to have some amount of time in order to represent that value. And the more different values you want to represent, the slower your system is going to run. And the neuron is so slow to start with that to represent 100 different values is going to make it uselessly slower. What that means, because of that, machine learning is not particularly viable in biological neurons, and I'll talk more about that in a little bit. And neurons are particularly bad at storing sequential information. And so this might be the most useful part of this presentation. You can write down this phone number. This is the phone number to the White House. You can phone that number and complain about anything you want. But you might think that you want to recite this phone number, you have a bunch of neurons representing the digits, and then you have a neuron or a cluster of neurons representing this, and you're going to fire this neuron, and these are all going to fire. And the problem is, if you just do this, all of these neurons are going to fire at essentially the same time. And it's very difficult to think about sequential information without a structure that looks more like this. And you get these sequencers or chains of neurons, and you have to have 2 neurons for every step in the chain if you want to be able to control the speed of the playback. And so for example, if I wanted to say 202 or 202, that's a lot of different sequential neuron firings. And so you end up just storing sequential data like that. And this leads me to graphs. And for those of you who haven't been down this road, a graph is a collection of nodes connected by edges. And for example, you can represent the statement, yellow is a color. And the arrow in this case has it has an arrowhead indicating a direction, because that means that color is not a yellow. You got to know what direction the link is. But in a graph in general, you can follow the links in both directions. So I can say, name some colors, and you can say yellow. Graph can be a lot of stuff. And you see all of these pictures with circles and lines and stuff. You can make a lot of graphs do things you want. And one of the most common in AI is called a knowledge graph, and I'll talk about that. It also goes as a semantic network. There may be some subtle distinction that I'm not sure about. The neural network could be a graph. Anything you want can be a graph. Your brain could be a graph with neurons representing the nodes and synapses representing the edges. A computer program could be a graph, which means that you could build a graph with the program that defines the graph as its content and have a very interesting philosophical conversation about that. And we know that there has to be some amount of data area in your brain that is a graph, because you can know that yellow is a color and blue is a color. And from that, I can say, name some colors, and you can say yellow and blue. Okay, you already knew that. That's not special. But now, how many of you are in computer science? Okay, quite a few. So you've all seen examples with foo and bar. I can tell you that foo is a color and bar is a color. And now you can say, name some colors, and you can say yellow, foo, and bar. I trained your mind with a single instance of information, and you knew the reverse of that information instantly. And that says to me that there's got to be a graph. In fact, we could talk about foo as a color and bar as a color for quite a while. And if I say that, you might actually remember that foo is a color and bar is a color, especially now that I've said it 3 times. And you probably can't remember the phone number, because phone numbers are sequential, and that's a lot tougher. So the question is not whether or not there's a graph, but whether it's a small graph and a lot of other stuff, or a big graph and a little bit of other stuff. Of course, you got to have the actions and inputs and sensory and other stuff in addition, but that's the same regardless of the graph amount here. Well, let's ask, well, suppose your entire neocortex was a graph. And what we want to ask about is, so you go to the neuron simulator and you say, this is what it would take to build graph nodes. And essentially you can build as many nodes as you want in the simulator. And in a minimal requirement, I could build a graph with 8 neurons per node. And you can't use 1 neuron per node because synapses are one directional. And I already told you in the previous slide that you got to be able to traverse this information bidirectionally in order for it to be useful. So the minimum I could come up with was 8 neurons per node plus an additional 2 neurons for every edge type you want. And I only programmed up 2 edge types, but you can add as many as you want. And a problem with this design is the failure of any single neuron or any single synapse will cause the system to fail. And we know that the brain is highly redundant and highly capable of surviving various kinds of failures. Neurons fail all the time, and they don't seem to bother you very much. And so this implies, let's give a rough estimate, that it's 100 neurons per node, because that gives you not only some redundancy, but it gives you the ability to track how recently a node was used, so you know when to forget and things like that. And if you do a little bit of division, if there are only 16 billion neurons, and I say only advisedly, 16 billion neurons in your neocortex, that says that you've got a maximum of 160 million nodes. And that may sound like a lot, but Wikidata is a knowledge graph. It's got about 100 million nodes and 1 billion edges, and it contains a ton more information than my mind. Now, my mind does store some stuff that is not in Wikidata, but I'll show you Wikidata in a slide or two here. But if we're talking about a system of 160 million nodes, I can put that on a desktop computer. That doesn't require supercomputers and the largest computers in the world. It's just not that big a deal. So the only things you can do in a graph, graphs are pretty simple. You can add, delete, and modify nodes. You can add, delete, and modify edges. And then the key is that you can search it millions of ways. And In the brain, it's likely that there are not very many ways that you can search, but a lot of redundancy. So this is what a node looks like in Wikidata. This is the node for yellow. And all of this is the data that's actually in the node. And then what they call statements like yellow is a color, those go on for pages. And this highlights a distinction between the knowledge graph and the information that's in your brain. In a knowledge graph, when you put in some information, you assume that it's correct and you want to keep it a long time. In your brain, you got this constant flood of incoming information, and in order to do things like, well, now I know that the audience is behind me, and now I know you're in front of me. To do transformations like that, you've got to have a lot of short-term memory, and you've got to be able to store a lot of things for a very short period of time, and you have to forget what proves not to be useful. And so it's a kind of a difference in strategy. You need to have real-time information, and here's the real bugger. In your brain, the nodes and edges cannot contain any data directly. If they did, our understanding of the brain would be entirely different. We'd open up the skull and we'd see all of these labels, and we'd see that the mythical neurons flash whenever they fired, and you'd know how the brain was laid out. But in the brain, we're pretty sure there aren't any Unicode strings, there aren't any floating point numbers, and there aren't any images as such. But you end up with an abstract kind of a mechanism like this. Let's say this is the abstract node representing yellow. And yellow is a color where there's some sort of abstract node representing color. And if you see something yellow, it will fire this abstract node of yellow. And it connects to things that are yellow that have lots of other nodes. You have a mental model that shows where you might have a couple of bananas in your field of knowledge. And then you get to words, and the words that represent yellow, you might use the word yellow or the word amarillo or the word gulp or the word coward. Could mean a lot of things. You can have a lot of words associated with something, and remember, you have no data, so you don't know what these words are either. And so we'll look at this one and we'll say a word must have at least a pronunciation, and if you can read, it's got to have a spelling. And so you have to have one of these sequencers like for the phone number, because pronunciation has to be sequential, because I can say yellow or I can say yellow. And this information is used in an incoming auditory cortex so that you can understand the word when you hear it. So you have to have this information, and this will percolate up and fire the abstract node yellow. You've got to be able to run it the other way, so this will pipe out to your cerebellum, and you'll go through the complex mechanism of perhaps hundreds of muscle contractions to be able to say the word. And then, of course, if you can read, now we have the spelling for the word. And for each of the letters that you can spell, you've got to have the visual input for the word. And you can I put in Y and E, so you get an idea that you've got 3 segments for a Y and 4 segments for the E, and maybe you've got some sort of mechanism for remembering that. And then you want to be able to output this information. So the Y might be keyboarded, it might be written by hand, and when you stop to think about it, when you're taking notes, you don't really pay attention to whether you're writing or typing. It's just fully automatic. You think your thought and it comes out and it goes to the paper. You don't have to pay attention. But we can also look at each of these letters as being an abstract node in its own right, with a word which you can say like Y, and it has a pronunciation Y. And so you can see that in your brain, you've got this network of stuff, and you don't know what any of it means except by context. And so you've got all of this context, and context is everything because the nodes themselves don't have labels. So we're going to talk about a bunch of the software shortcuts that we can have, like handling sequential information. In a computer, all the information is inherently sequential. You can't store something in a computer without an address, and the address has implications of data that came before and other data that comes later. Another shortcut is 3D vision. You can have, with your two eyes, you can look out at something and estimate in your mind how far away it is. And you do that with millions of neurons. And I can do it with a computer and a couple of lines of trig, and it runs a whole bunch faster than it can possibly run in your brain. I wanted to talk about the robot coordination, and I never miss an opportunity to add this Boston Dynamics video clip because it's so popular. But the key to think about is that it gets this wonderful fluid motion, which essentially replaces the 56 billion neurons of your cerebellum, and it does it without thinking about neurons, because the guys that write the program know about forces and physics and feedback, and they can do that in a couple of microprocessors. And so the idea that you need a supercomputer in order to emulate all of the neurons and synapses in a brain is simply unrealistic, because you can take all of these shortcuts and eliminate vast quantities of stuff and get past it. Of course, we can represent our graph in software structures instead of in neurons, and that's a whole lot more efficient because we've got lists and structures and hash tables and can do all kinds of good stuff. And we can put labels and values in our nodes. And so we don't have to go through that whole rigmarole that I just showed you of figuring out what yellow means, because we can just write yellow in the header of the node and know how to spell it and know how to say it, etc. Machine learning. We can use machine learning where we haven't figured out how to answer a problem. And some people think that I'm not particularly in favor of machine learning. And the truth is that if I'm willing to use trig to do three-dimensional calculation, I can't fault somebody for using machine learning to do some sort of a visual interpretation. It's all just a software shortcut that may or may not have anything to do with the way your brain works, but accomplishes a similar task. And finally, I said, well, we got a maximum of 160 million nodes, but I don't know how many nodes it really takes to be generally intelligent. Maybe I can build a system with 1 million nodes that's smart enough to work at McDonald's. Ask me in a year. I'll have a much better idea on that one. So where does all of this lead me? Well, the amount of programming you got to write for AGI seems like it's going to be manageable as soon as we figure out what it is, and that could be happening at any time. The size of the data that you need to represent is manageable. The hardware already exists to handle networks of hundreds of millions of nodes. That's not a problem. We've got all of these software shortcuts that we'll be able to take, again, as soon as we figure out what the AGI program really is. And then we'll get to the process of how we're going to create it. AGI emergence is going to be gradual. And the reason that it's going to be gradual is every time we start to approach AGI, we get some AGI-ish kind of a capability that is marketable in its own right. So I produce something that has an improvement in the way your Alexa understands you, and everybody's going to love that. And somebody else produces something that's got better vision that they can use on a self-driving car, and everybody's going to love that. And as we approach actual human level intelligence, everybody's going to love it, because all of these little pieces are going to be marketable, and the more we attach them to each other and the more they can interact and have their context, the better things are going to be. And finally, as we approach human level intelligence, nobody's going to notice. And at some point, we're going to get close to the threshold, and then we're going to equal the threshold, and then we're going to exceed the threshold. And at some point thereafter, we're going to have machines that are obviously superior to human intelligence, and then people will begin to agree that, yeah, maybe AGI exists, but it's not going to be a specific time that happens at a specific place. And so the nut of this is that my overall conclusion, AGI is inevitable and possible and sooner than most people think. Could be as little as a couple of years. And I want to thank you for your time. I want you to visit our behind the scenes, which today is just out in the little restaurant outside the bar here, that you can see our little robots running around, and I'll be happy to show you our internal graph structure as it is. Robbie Robinson's presenting a neurally plausible graph structure for AGI, and I'd like you to submit questions, or if we have time, we can take some today.
Right, I'm sure we have lots of questions for Charles after that riveting talk. I'm going to go online first. Alex, I believe you have a question for us online. Hi.
Hello. Very interesting talk, Charles. I thought it's kind of interesting that you were looking at the brain architecture, and I was particularly fascinated by your nodal representation with neurons. And so I work in the area of brain-inspired stuff. I work in spiking neural nets, and you did show rate potential and the crossing of spikes, for example. So a couple of questions raised in my mind, and especially in your earlier neural implementations, which I actually do think need to be answered, because I think learning, without necessarily saying a machine learning approach, is critical to address if you want the inevitable AGI. And again, that might be an interesting discussion if you disagree, but I do think getting the learning process is the hardest and perhaps most unstable part. So my question for you is, what was your learning type? You did show the STDP curve, so pardon me if I missed some detail. Did you rate code the neurons? Were you learning in pure spikes? Because if so, which would be more brain-like and efficient, it's extremely difficult to learn, especially time-varying data. I can't even imagine learning a graph system with spiking neurons, even though it could be done. And then again, some other things, because again, if you've heard of Spawn and Nango, that also has some tools, for example, when it comes to neural modeling. So did you do things like, how did you address the reward part with a basal ganglia? How did you deal with catastrophic forgetting? Because even spiking nets, they do exhibit this. So I was just curious to know about your learning process, and did you really work in spikes or rate coded, and how did you deal with reward signals and catastrophic forgetting? Sorry you can lump them all together as one super question.
Sorry.
Okie dokie.
Okay.
Okay, let me address the question. I mean, you asked a whole series of wonderful questions, and let me address a couple of them. When I showed the little picture of the graph, and we had the horizontal rows that represent nodes, all of the diagonal synapses in the table represented Hebbian synapses, and they were what represented the connections of the nodes to one another. And we have to presume that you have clusters of thousands of nodes that are fully interconnected, and by simple association of Hebbian learning and Hebbian synapses, you can make any connections that you need to make. You need to have a memory controller, sort of a system. And let's just imagine that it's the hippocampus that does that for you, that will be able to, and I mean, speaking just without any experimental data to prove that, but you have to be able to do sequential things, like you have to be able to make the node of parent to child, the connection from parent to child and the connection from child back to parent. You have to be able to create that. But if you are using simply a Hebbian model synapse, you can create that in fairly short order. And that was the model that we used in that process. And to some extent, having proven to ourselves that we could create a graph in spiking neurons, we then created a graph in a higher level language and didn't pursue the neurons much further, because the neurons were difficult to work with in software.
And slow, I imagine, too. It's very hard to simulate.
Yeah.
Thank you. I'll save other questions for later.
Thank you so much, Alex. Thank you. Right, who in the audience has any questions for Charles? It's working now.
Okay. You found the secret.
Anyone in the audience, any questions for Charles? Or has he just blown your mind?
Yeah.
One here, thank you.
Out of all the different modules that you're bringing into the brain simulator, what's the hardest one to incorporate?
You say modules or
Modules.
Modules.
I saw that long list of modules you have integrated.
Right. Well, let me back up to bring everybody else up to a speed. The brain simulator is a spiking neural simulator that's got all of these neurons and synapses, and it also has the ability to create software modules that you can create, simply outline a rectangular collection of neurons and say, when you get to this set of neurons, I want you to execute this high-level code. And so you can do anything you want in the high-level code. And for example, we have the module that is the graph, and we have the module that is a camera interface, and another module that's a speech recognition interface that simply gets data from a microphone and pipes it out to Azure for speech recognition. And by far the most difficult part of this process thus far has been maintenance of the mental model. So I look at you and I see you here, and now I'm facing this way, and I have to know you're over there. And now I come back and I see you again, and I have to know that you're the same person that you were the time before. And so we had a lot of difficulty in writing that, where you would look at something and see it, and then you'd turn and turn back, and the unit would be duplicated, or it would be in a slightly different location that had to be corrected. And we learned a lot in creating a mental model, but it's reasonably accurate now, but it's a ton of code to correct for all of these potential small errors that creep into the process.
Thank you so much, Charles, for that fantastic talk. It's so inspiring as well and uplifting, and I love your message that AGI is inevitable. Does everyone in the audience agree AGI is inevitable? Yeah, we do. Show of hands. No, Ben doesn't.
Ben doesn't. What do you think, Ben? Oh, okay.
Ben says highly probable rather than inevitable. Always accurate to the absolute umpteenth degree. Right, so big round of applause for Charles. Thank you so much for a fabulous talk.